All right, so the next thing is, evidently I'm interested in part C. Okay, so what is the magnitude of the impact force? The impact lasts only 1/100th of a second. All right, so we want to express the force in terms of pounds. What's the magnitude of the impact force, if that's the case? All right, so what do we know? Impulse theorem. Impulse is going to change momentum. All right, so we know the duration of the impact. The impact is going to last for 1/100th of a second. That's what we end up getting. All right, so we're interested in the magnitude of the impact force on the person in this case. You end up getting a number like that. Change of momentum of the car is going to be the same in opposite direction, so that's going to give you the reaction force. Notice the action and reaction force are the same, just as expected, and they're about 40,000 pounds. All right, that's it. Okay, that's how I was generating those numbers, the earlier portion of this course. So that's how it is done. Okay, so the thing I want you to know, that this was a lot of math for you guys, for those of you guys taking college physics, and you guys are taking college physics. Okay, math is not that important, but I want you guys to be able to interpret the meaning of what we just saw. Okay, so that's what I want to focus on right now.
Next, Detective Wallstead
which means that I want you to be able to interpret formulas, those two formulas that we came up
revealed
with.
the secret behind this game, where you have to get the ball to stay in the tub.
There's one game that I see very frequently, almost at every carnival. It's that bushel basket game. And that just annoys me because I'll stand back and watch people walk up and get cheated, because you can't win the game the way it's set up.
You're not going to be able to win this game the way it is set up.
The player stands back and
Why?
such a distance.
Because this game is unwinnable. Okay, I kind of hate what I just said. Obviously, it's kind of funny at first glance, but seriously, you guys, when I ask you these kind of questions, some of you guys answer it just like that. It's kind of weird. When I say,
And the angle.
why is it that you cannot win this game? And some of you guys say, because it's unwinnable. That's not what the question is, guys. That's not the answer to that question. The question is, why is it that you cannot win this game? That's what the question is. You can't just answer it because it's unwinnable. All right. What makes it unwinnable is what the question
The
is.
basket, you cannot win.
So the question is, why not?
And the ball won't stay in there.
So the reason why it's unwinnable is related to
You want to give them the impression that there is a chance
something that these guys understand really well. And obviously, most of you guys lack that understanding.
to win. And it's a good chance. And
To cover his face.
in reality, there's no chance to.
There's no chance. You cannot win that match. The only reason why they're going to make it look like you got a little bit of a chance is because they will leave a ball in there.
Sometimes the carny will reel you in with a free throw, but you can bet that's usually rigged too.
It is rigged. So the question is how. And as soon as you have to throw that, he's going to remove the ball.
It's a classic scam right there. What he does is he puts a ball in ahead of time and tells her,
And he made it, from that angle, he made it look like it's going to stick.
go ahead, you throw one in for practice. And what happens is her ball goes in, hits the one
The reason why it went in, because he ended up hitting the side. So the motion got transferred in that direction.
that he put in there, and
From the angle that you're throwing.
hers will stay in. But out comes her money. Out comes that other ball, I guarantee it.
And now here's another game of chance. Fat chance is more like it.
Yeah,
All right, so
because this game was to knock down both Coke bottles with one
you're not going to be able to knock both of them down.
roll of the ball. It
It doesn't matter how fast you throw.
can't be done because what the guy
Okay,
does is he'll actually nudge one of the Coke bottles slightly in front of the other, maybe
okay, and then how did that work?
an eighth of an inch, quarter of an inch. So what happens is when you roll the ball into it like that, the ball hits one of the bottles there, you can clearly see one
Okay, and then you can pay more money and then try to go faster and
in
faster.
front of the other. There it went. The energy from the ball was absorbed in the first bottle, leaving nothing for the second bottle.
That's cute.
All these little scams add up to big money.
So why is it that it doesn't matter how fast you throw the ball, you're not going to be able to knock down both of them? Okay, so how come you can never win these games?
Get the ball to stay in the tub.
First one, you will never be able to get the ball to stay in the tub or the bucket in the case,
Fat chance is more like it.
and you will never be able to knock down both Coke bottles at the same time.
Yeah, because this game.
All right, so how do I know that? How do they know that? Okay, so take a short little break and then let's have a conceptual discussion. And then I'll point out which problems to focus on for you guys, because I don't want you to focus on everything. You guys are taking college physics, not the university physics. There are particular problems that I want you to focus on, and there are particular things that I want you to know conceptually, understand conceptually inside out. Okay, so I'm just going to put emphasis on those things. All right, so go ahead.
Are we going to review the conceptual for chapter 6, 7, and 8?
Yeah, we will right after this.
Okay.
Yes, we will. All right, so take a 5-minute break. So the reason why I'm giving you a break is because I have to connect my iPad, so it takes about 5 minutes. Okay, so that's the reason why. All right. Okay, do you want to continue? Okay. All right. 3 cases that we need to look at in terms of collisions. All right, so you guys need to know this stuff. There are 3 cases. We're going to be looking at 3 different collisions. All right, so let me just grab this, put it to the side. Okay, case number 1. Is going to involve a huge mass colliding with a very small mass. Okay, so MA, and you have your MB. MA, this is the initial speed of A. Okay, so I'm going to end up using the same terminology. All right, so this is before impact. So the question is, what happens after impact? All right, so what happens to the speed of A right after impact? All right, so underlying assumption here is MA is going to be significantly larger than B. Example is, this is like the train, and this is like the person getting hit by a train. All right, so which means that we will have to kind of interpret these formulas. Okay, so what I'm going to do, I'm going to grab this equation, and then I'm just going to interpret it. Okay, so here's the speed of the, we're going to be looking at the speed of the train right after impact. All right, so this is the speed of the train. All right, if mass of A is significantly more massive than B, what happens is you can literally ignore the mass of the person, all right, in that computation. That's what it means. A is so much bigger than B. If that's the case, adding and subtracting this is not going to make that much of a difference. So what you can do is just ignore it. This becomes ignorable. All right, so when you ignore it, what's going to happen? So here's the speed of this train. All right, and then here's the mass of the train. Here's the speed of the train just before impact. All right, so that term is going to become, these 2 will cancel. So which means that the train speed is not going to change. It's going to be more or less the same as 60 miles per hour. Kind of expected that. All right, so next question is, what happens to the person? Well, once again, just remember this one is ignorable. Just ignore, too small, because it's way too small in comparison to the mass of the train. So because it becomes ignorable, now what do we have? All right, so here's the speed of the person, 2 times the speed of the train divided by 2 times the mass of the train divided by the mass of the train, multiplied by the speed of initial speed of the train. All right, so you got your common terms. Boom, boom, they will cancel. All right, so what do you end up getting? It's going to be 2 times the speed of the person, 2 times the speed of the train. All right, so the speed of the train is not going to change. And now the person is moving nearly double the speed of the train, nearly. All right, so the person is going to be moving nearly double the speed of the train. Okay, so this is case number 1. Case number 2, what if the masses are the same? Okay, so you got 2 billiard balls colliding with each other. So what if the masses are exactly identical? MA, MB, we will have identical masses. Once again, A is the one which is moving. All right, so yeah, once again, we will get to use the same equations. Okay, so I will get to use this one more time, so let's copy that for future usage. Okay, guys, masses are the same. Because masses are the same, what do you think we will end up getting? MA is the same as MB. All right, so we can express them like that. So here's the speed of the incoming mass right after collision. Remember, MA and MB will be the same as B, so it's going to be M minus M divided by M plus M times, here's the final speed, here's the initial speed of the mass A. All right, so what do you end up getting? M minus M is going to be 0, so this term is going to go to 0. All right, so the incoming ball, billiard ball in this case, is going to come to a stop. So what happens to the target? What happens to the speed of the target? All right, so now you got the second equation. Remember, M, M, M. Okay, so In the numerator, you have 2m1. Okay, not m1, just m. In the denominator, you have m plus m. And here's the speed of the incoming. Okay, m plus m is going to be 2m. And then you have 2m divided by 2m. So that's going to give you 1. So which means that the second mass is going to travel at the speed of the first one. Okay, remember the Coke bottle? The reason why the Coke bottle, if you have two of them next to each other, that Coke bottle has exactly the same mass as the ball does. That's the reason why it doesn't matter how fast you throw it. Whatever the speed that you throw it with is going to be the speed that's going to get transferred to the Coke bottle. And then obviously the incoming ball will come to a complete stop as the Coke bottle is going to move forward. There's no way you can hit the second one, right? Because this will come to that stop. And the Coke bottle is going to move at the speed of the incoming ball. All right, that's it. All right, so that's how the trick works. The bucket trick works on the following premise. Okay, so now what you got is the incoming mass is going to be significantly smaller. All right, so the incoming mass is going to be significantly smaller than the target mass. All right, so MA is going to be smaller and MB is going to be humongous. All right, so this one is going to be big. So MA incoming, it's incoming at a given speed. Is going to be much smaller than N sub B. Okay, so what does that mean? Which means that now this is going to become ignorable. Ignore this portion. And now you will try to ignore this portion. All right, that approach is not going to work too well. So what I'm going to do is, because this is going to be, MA is going to be significantly smaller, I'm going to just make a little notation. I'm just going to assume that it's so small that it's almost non-existent, which means that this mass is going to go to 0. Okay, so when that goes, that thing is just so massive, which means that it's going to barely move. It's like hitting a wall, guys. All right, so throwing a ball up against the wall, that's what it means. The wall is not going to move. The target is simply so big. It's so massive. The target is B. Target is so big. It's so massive that it's not going to move. Or you can assume that it's infinitely massive regardless. There are two ways of doing it. That's one way of doing it. It's so small that we will get to ignore the first mass in the first one. So what happens to the ball? All right, so it's not so massive. So you got B divided by N. The mass of the second one divided by the mass of the second one. All right, so they will cancel. So which means that the ball is going to bounce at the same speed. In the opposite direction. Ball is going to bounce in the opposite direction. Okay, so hence the reason why every time you throw the ball into the bucket, it's angled in such a way that you're just hitting it against the wall. Incoming speed and the outgoing speed will be the same. It's not going to move. Only way it's going to stay in the bucket if you place a ball which has the same mass. Incoming one is going to hit this one. So what happens is the momentum is going to get transferred to this one. Depending upon how you hit it, this may end up bouncing out of the bucket, but this one is going to stay inside the bucket. Without a ball inside the bucket, you are throwing it up against something really massive. All right, and so mass of this is significantly smaller than this one is. So the wall or the bucket is not going to move. Instead, the ball is just going to bounce out of the bucket. So that's what's going to happen. All right, so here's the final speed. Okay, so we got 20 minutes. Let's go over the test.